Take a physical book, strike a match, and set it on fire. I let it burn until there is nothing left but smoke and ash. What happens to the information inside that book? To our eyes, the book is gone. But in basic physics, information is strictly conserved. If you could somehow collect every single piece of ash, every wisp of smoke, and every photon of light emitted by that fire, you could, in principle, perfectly reconstruct the book. That conservation law holds true for almost anything we can test. What happens if instead of a fire, you throw that exact book into a black hole? Because nature demands that information cannot be destroyed, tracking that lost book forces us to test the absolute limits of how reality works. To understand why this poses a massive problem, we have to rewind to the 1780s. Two thinkers, an English clergyman named John Michell and the French mathematician Pierre-Simon Laplace, independently started exploring a thought experiment. They were thinking about a concept called escape velocity. This is simply the speed you need to travel to completely break free from an object's gravitational pull. For Earth, that speed is roughly 8 miles a second. If you look at something much larger, like our Sun, the gravitational pull at the surface is vastly stronger. To escape it, you'd need to be moving around 400 miles a second. Michel and Laplace wondered what would happen if you kept going. They imagined a star so massive, with gravity so intense, that the escape velocity actually exceeded the speed of light. Even light itself wouldn't be fast enough to get out, making the star entirely invisible. That historical idea laid the groundwork for what we now call a black hole. It is an inescapable cosmic vault, where once something goes in, nothing can return. Let's trace our book as it falls toward this vault. First, it crosses the event horizon. This is an invisible spherical boundary, separating the external universe from the interior of the black hole. According to Einstein's theory of general relativity, if you were watching this book fall from a safe distance outside, the event horizon is a place where time itself appears to stop completely. Deeper inside lies the singularity. People often picture this as an infinitely dense point in space where the massive star collapsed, but it's actually more accurate to describe it as a moment in time. In fact, it's the absolute end of time. Under general relativity, our book is now permanently locked inside a region so distorted that our standard maps of space and time completely break down. For a long time, physicists assumed that was the end of the story. But a 1974 breakthrough by Stephen Hawking showed that black holes are not eternal prisons. He discovered that they actually have a temperature, and they glow by emitting particles. To see how, we have to zoom in right at the edge of the event horizon. Here, quantum mechanics tells us that pairs of entangled particles, twins linked at the quantum level, constantly pop into existence out of empty space. Usually, these pairs immediately merge and vanish. But right on this sharp boundary, it can happen that one of those particles falls inside the horizon, while its twin manages to escape out into the universe. By escaping, that surviving particle steals a microscopic amount of the black hole's energy. Over billions of years, this glowing mist of escaping particles, known as Hawking radiation, slowly drains the mass away. Eventually, the entire black hole shrinks down and vanishes completely. This creates an enormous problem for physics. If the vault physically disappears, leaving nothing behind but a cloud of radiation, where did all the stuff inside it go? Think back to our burned book. The black hole that swallowed it has evaporated. All we have left is that cloud of Hawking radiation. We have to ask, is the information from our book gone forever? This precise conflict is known as the black hole information paradox. It is a severe clash between our two best descriptions of reality. Quantum mechanics dictates that information is always conserved, but general relativity suggests the vault holding that information was destroyed. The modern consensus among physicists is that the universe did not delete the book. We now believe the information is scrambled, but carefully imprinted inside that leftover Hawking radiation. Reconciling these two views is the primary challenge of modern physics. It requires a single, unified theory that explains both the gravity of a star and the behavior of a particle. So, what underlying mechanism possibly allows that faint radiation to store the complex information of everything that ever fell in? The answer points physicists toward an idea called emergent spacetime. Much like liquid water is made of individual H2O molecules, the fabric of space and time might not be a starting point of the universe. Instead, space and time likely emerge from much smaller, unknown quantum pieces woven together through entanglement. Black holes are the only laboratory we have to study this. They are real, observable objects that force us to ask how space and time are constructed. By pulling at these intellectual threads, we are starting to catch a glimpse of the deep underlying structure of nature. If we can prove space and time emerge from something deeper, we change how we understand the very beginning of the universe.